everybody. My name's Phil Hasnip. I'm from the University of York, and the thing I'm going to talk to you today is some scientific software that I developed called CASTEP. And I'm going to tell you a little bit about the approach we're taking to offload CASTEP to GPUs, which I've called the Prime Directive, and you'll see why later on in the talk. So first, a little introduction about CASTEP. So CASTEP is what we call a first principles materials modeling program. So you might see first principles materials modeling software on an HPC facility near you. It might be CASTEP, it might be Quantum Espresso, it might be VASP, it might be Abinet. There are various implementations, but between them, they use a substantial fraction of HPC compute globally. In the UK, where I am, it uses about 40% of the compute cycles of the national machine. So a reasonable question to ask is, if I'm using 40% of our resources, what does it actually do? Well, what it does in short is it tries to predict the behavior of materials without having to know what the materials do beforehand. So in other words, I want to know whether a material bends, for example, easily, or conducts electricity, or is blue, and I want to do that without knowing anything about the material apart from perhaps its chemical composition and an idea of what the atomic structure is. And to do that, we need to use quantum mechanics, and we need to model the electrons in the system. But I'm not actually going to talk too much about that today. You can always ask me about the details later on. Today, I'm going to take a higher level look at what CASTEP does, and this is my cartoon of what it does. So the idea is that we take the chemical elements of the atoms involved and roughly where they are arranged in the material. We take a particular quantum physics model. The kind that I'm talking about is actually called density functional theory, and I feed those to CASTEP, and then CASTEP does all of the work for me. So CASTEP takes those rough positions and it tells me what the optimal positions are, so the optimal geometry. It tells me about the electronic properties. Is it magnetic or not? Is it a metal or an insulator? It tells me about dynamic properties. So, for example, what's the infrared spectrum? If I went to my friendly chemists just across campus where I am in York, what would they measure if they put that in their spectrometer? Now, this is a cartoon, and in some ways it's an aspiration. This is how we'd like CASTEP to work. We would like the scientists to just be able to ask the question of what is this material like, and not have to care about, for example, what computer they're running on. Now, CASTEP has got quite a pedigree. The new CASTEP, in inverted commas, was written in around about 2000, 2001 by 6 people over 2 years. So there's 12 years worth of effort. And that was 20 years ago. So there's been a lot of development, optimization, new functionality over 20 years. It's currently somewhere between about 600 and about 750,000 lines of modern Fortran with MPI and OpenMP. And it works very well on CPUs. It has good parallel scaling, and it's produced a lot of good science. We get about 1,200 papers a year from people who use CASTEP to solve scientific problems. But of course, now we're interested in heterogeneous computing. GPUs have tremendous compute power, but we want to know, how can we use the compute power offered by GPUs, but without throwing away the work on CPUs? So we don't want to throw away 2/3, 3/4 of a million lines of code and 30 years of effort and start again. And whatever solution we come up with for using GPUs, we still want to be able to run on CPU systems, from laptops and maybe even mobile phones, all the way up to large CPU facilities, perhaps even Fugaku. And the option that we've chosen is OpenACC. Why have we chosen OpenACC? Well, it's a directives-based approach. And that means that we can take the CPU code base, we can decorate it with what look to Fortran compilers like comments, but which include descriptions of what we're doing that enable the compiler to generate code for the GPU. So in the same way with OpenMP, of course, it allows us to have a single code base. And that's our goal, that we have GPU acceleration without disrupting the code that we have that works so well on CPUs. And in fact, it could even be that some of the code we still execute on CPUs where there's a performance advantage or where we need more memory than is available on the GPU or whatever the accelerator might be. And so I've called this talk the Prime Directive after the Star Trek principle of non-interference. So this is a GPU approach where we don't interfere with the CPU operation. Okay, that's the goal. If you're interested in details, we've recently published our first paper on the GPU port earlier this year. I've put the reference here, and I'll put it again on the slide at the end. Now, that's a great dream. But of course, the immediate question is, well, what performance do we get doing this? So I've run a benchmark calculation here on the facility Bede, which is the northern UK GPU facility. It's a Power 9 architecture from IBM with some 32 gig V100s. In fact, each node has 4 V100s and 32 compute cores. If you're familiar with Summit, for example, in Oak Ridge, then this is quite similar. Fewer CPU cores and 4, not 6 V100s, but basically the same architecture. Now, this is the time per iteration of CASTEP, and this is on CPUs. So if I run with the GPUs when we did our first work, then this is what we get. This is literally like for like with 30 cores of the CPU for one node versus 30 cores of the GPU, and similarly for the scaling. Okay, so this is a completely fair, using all the resources on 1 and then 2, 3, and 6 nodes, CPU only or CPU plus GPU. And you can see that right across the board, the GPU performance is really quite strong. And we were very happy with this. This was a code base which worked on the CPU and the GPU. We'd had to do a little bit of refactoring, but we checked the refactoring back into the main code base. So we had a single code base. We published this, and this is what you'll find in the paper I referred to earlier. But actually, when we analyzed it, we realized we were doing quite a lot of data copies that we could reduce. So in the last few months, we've actually worked a little bit harder on extending and optimizing the OpenACC regions, and we now get this time, which you can immediately see is a lot better. And I apologize that I haven't had time to run this at 6 nodes yet. That would have been the perfect icing on the cake. Now, it's quite hard to see from this exactly what speed up we get. So let's take the ratio of these GPU times to the CPU time and look at the speed up. And if we do that, we see that, of course, the CPU has a speed up of 1 because that's the reference. Our initial GPU results give us a speed up of over 2 consistently. But now with the refactoring, we're seeing speed ups of over 5. And actually, this isn't the end of it. We've done analysis and profiling, and there's still some data copying going on that we think we can avoid. So we expect this to do nothing but get better over time. And our goal has always been to keep this single code base. Now, I'd be lying if I said that there were no challenges involved in this work. I've already mentioned the data movement and the need to minimize data movement. Bede is quite a friendly architecture for that because the CPUs and the GPUs are joined via fast NVLink. When we move to x86 architectures, we have 2 challenges there. The first is we're typically on a PCI Express bus, which is a bit slower, so the data movement is more important. And the other is that if you take something like an AMD Rome chip, then it really has quite impressive headline performance just on the CPU. A dual AMD Rome with 128 cores has is quite a powerful beast. So it becomes even more challenging to use the GPU to get efficient and quick improvements. But data movement is made harder when we have a well-engineered code, and we pride ourselves that CASTEP is quite a well-engineered code from a software engineering perspective. But encapsulating the data in the code makes it rather harder to optimize the data movement, because now we want to move data to the card well in advance of needing it. but the data objects might not even be in scope. So we're trying to go through the code now and work out how can we bring objects into scope in a way that is natural and transparent to programmers, so that we don't have a GPU dedicated team and sort of branching off from the main CPU development. Related to this is how can we use the GPU most effectively when we have multiple CPU cores? So I've already shown you 32 cores sharing 4 GPUs. What's the best way to share them? And in particular, sometimes the MPI processors have the same data, it's replicated. I might be multiplying 2 objects together, let's say A and B, where A and B are arrays, but it might be that A is the same array across the processes and it's B that's distributed across the MPI processes. So is there a way that we can transfer the array A once and have it live on the GPU as one copy and share that amongst the MPI processes? This is very difficult to do in a standards compliant way in OpenACC, and this is one of the top of our wish lists. And actually memory is one of the main problems, and the other bit that hits us is device memory in OpenACC maps to host memory. So if I have an array on the GPU, I have an array on the CPU. And as we port more and more code into OpenACC regions, we have more and more things happening on the GPU, we're starting to want to have temporary arrays on the GPU, and we don't need them on the host. And actually, sometimes having them on the host would be a problem. Some of them can be quite large, some of them are replicated at MPI, and it can actually tip us over our RAM limit. There are ways in OpenACC of doing this, and in fact, CUDA Fortran has some attributes too, but actually they're not widely implemented. And in general, if I allocate an array on the GPU and I tell it to only do it on the GPU, actually a shadow version is also allocated on the CPU as well. And that's caused us real problems. So that's a whistle-stop tour of what we've accomplished so far, how we've done it in a broader brush way. And the take-home message that I'd really like to say is that OpenACC is really an excellent way to doing GPU acceleration. It lets you port bits that you know are compute intensive and to just focus your efforts there and then slowly expand them. So you can get quite a useful port, get people using GPU machines quite quickly. Optimizing is much more work. And actually, the data movement is a problem. And the more careful you've been about your software engineering, the harder it is. So the more you've abstracted things away, the more you've wrapped things into data objects, the harder it can be to get the data movement right and in the right places. And we've illustrated that most recently by the difference between our current development version with its 5 times speed up, with the paper that we were very happy to publish earlier this year with a 2.2 times speed up. And this is identical benchmark on identical hardware with identical software stacks. It's literally just optimizing the data movement that's given us this. If we look at the difference in the memory bandwidth between the GPU and the CPU, the difference is about 15, I think. So actually, there is a theoretical limit, because we're probably memory limited, of about 15. So there is still this scope to take 5x upwards. And with that, I should wrap up. I must thank the people who've done the work. So Matt Smith, now at York, formerly of Barcelona Supercomputing Centre and before that at Cambridge. Ian Tamarus, who's at Cambridge. Ed Higgins is a research software engineer based at the University of York with me. And we've had a lot of support from NVIDIA and from hackathon teams, particularly at Bede and at Oak Ridge. So with that, I'll say thank you very much for your attention.